Motion of bodies when connected by strings. Earlier contacting bodies we have discussed, and now we will be trying to understand if the bodies are connected with the help of a string. So for this let us consider two blocks. Again, see block 1 of mass m1 and another block of mass m2. Both are connected. And let us suppose that the two masses are connected with the help of some string. So clearly, if you suppose that some force F is exerted on mass m2 and these two m1 and m2 are connected with the help of a string, then some tension will be created in the string, and that tension will be T. Okay, let us suppose the tension created in the string be some T. So as the force is applied towards the right side, both blocks will be accelerated towards right side with same acceleration, that is A. Okay. If you observe that, you can also see that which is simply I am telling children, clearly we have m1g, its weight is acting downwards and the normal reaction force on the first body be r1 upwards. Here m2g, if it is kept on some smooth horizontal surface, m2g and the normal reaction force is R2 upwards. But these two forces, that is R1 is balanced by M1G and R2 is balanced by M2G. There is no net effect. So the only effect here lies is because of that horizontal force. So let us try to understand the same. Yes. So just all the upward and downward forces are balanced, so no need to bother about it. So let us now focus on the horizontal force. The acceleration produced in each block is found to be how much, children? So acceleration A is equals to F net by total mass. So what is the F net? The net force acting on here is F and the total masses must be M1 plus M2. So this is the value of acceleration. Now let us try to find out the tension acting in the string. Clearly, if you observe the second figure, then because of the tension force T, the M1 mass is being accelerated. So from the second figure, we can directly say that T is equals to M1 times of A. This T is equals to M1 times of A. This can be written as M1 times of F by M1 plus M2. M1 times of F by M1 plus M2, because instead of acceleration, we replaced it with F by M1 plus M2, and this is found to be M1 by M1 plus M2 into F. That's it, children. Well, similarly, you can also solve the same if three bodies are connected in together with the help of a strings. Okay, let us take an example for three bodies connected with the help of a string. Let us discuss the same here. When three bodies are connected with the help of a string. So let us consider three blocks of masses M1, M2 and M3 be connected with the help of a string. M1, M2 and M3 are connected by the help of a string, two different strings. These two are joined by one string and these two joined by another string. Okay, and let us suppose that some force F is applied on mass M3. Some force F is applied on mass M3. Now the force, let us M1 and M2 is connected by a string in which some tension T must be acting. So let us represent this tension as some T1, and between M2 and M3 another string is being connected, and in this string some other tension might be acting, and let us suppose that tension as some T2. So here also, if you consider the first figure, downward force is m1g and the upward force is normal reaction, both are balanced. Second figure, m2g downwards and the normal reaction upwards balanced. m3g downwards and normal reaction upwards balanced. So both upward and downward forces are being balanced. Now the only net forces acting will be in the horizontal direction, that is towards the right side. And clearly we know that all the blocks, when force F is applied, all the blocks produces same acceleration. So the acceleration in all the blocks will be same. One, it's the same because of the same force applied on it. So, and this acceleration can be found by the net force acting on them to that of the total force, total mass. So what is the net force acting on it, children? The net force acting on that is equals to, the net force acting on this is nothing but F, and the total mass is m1 plus m2 plus m3. That's it. Well, you can even find the value of T1 as well as T2. Now, in order to find the value of T1, because of this T1, this mass m1 is being accelerated. So, clearly, from the above figure, we can say that T1 is equals to m1 into A. But the value of A is found to be F by m1 plus m2 plus m3. So, this must be m1 by m1 plus m2 plus m3 into F. That's it. It's as similar to the previous one, F by m1 plus m2 plus m3. Okay, whatever. So, tension T, the contacting force earlier guess, and now T1 is found to be m1 by m1 plus m2 plus m3 into F. If you would like to find out the value of T2, because of T2, these two masses are being accelerated, that is m1 and m2 together. Hence, the formula for this is, what are the two masses that is acting? m1 plus m2, okay, upon into F, into acceleration. Acceleration is given by F times of m1 plus m2 plus m3 into F. So, this is the value of the tension acting between the two masses, that is m2 and m3. You can even solve the same with the help of taking here as T2 minus T1. I'll try solving for the same for you. You'll get the same result, children. Observe the same. The right side force is found to be T2 and the left side force is found as T1. So, T2 minus T1 must be equals to M2A. The value of T1 is already, you know that it has M1 by M2 plus M3 into F. So, T2 is equals to T1 plus M2 into A. But the value of T1 is M1 by M1 plus M2 plus M3 plus m2 times of A. So, A is again, we can substitute the value of A as F by m1 plus m2 plus m3. So, if you take the LCM, we have LCM is m1 plus m2 plus m3, and numerator, if you consider F is taken common, then you are left with m1 plus m2 into F by m1 plus m2 plus f3. So, you got the same result. Okay, children? So, hence, you can find out the values of acceleration as well as the tension acting in the string according to the given numerical. Okay. So, now let us try to understand the similar models with respect to the bodies connected with the help of strings. Let us try to understand the motion of bodies connected by the strings with a few more examples, children. So, here we go. This is motion of bodies connected by strings. For this, let us consider a basic example. So, where we need to consider a body of mass m which is tied with the help of a string. So, a body of mass m is tied to a string. And let us suppose that the body is moved downwards. Which direction, children? This body is moved downward direction. So clearly, whenever an object is hung with the help of a string, no doubt its weight must be acting downwards and the tension T must be acting in the string as usual. And as I said that the body is set into motion in the downward direction, hence it's very clear that it is accelerating downwards. So now writing the free body diagram and the equations of this free body diagram, we have clearly the downward force is more when compared to the upward force, that is tension. Hence, the net force acting on this body can be written as sum of the downward forces minus sum of upward forces. So the net force is nothing but mass into acceleration. The mass of the block is given as m and the acceleration is a, must be equals to the sum of the downward force. The only force that is acting downwards is mg minus upward force here is nothing but tension in the string, that is T. Therefore, so after simplifying, bringing this minus T left side and taking the MA towards right, we have T must be equals to mg minus MA, or T can be given as m times of g minus A. Clearly from this we know that since the value of mg, so we are subtracting mg and ma, so clearly we have the tension T is less than, because this mg is dominating. As the mg is dominating, it is moving downwards. That means here the weight mg is clearly greater than the tension in the string. So whenever this mg is greater than the tension in the string, we feel as if the weight of the object is being lost, and we can experience the same whenever we simply leave a bucket inside a well, so we feel as if the weight is being lost. Okay, similarly the same example let us consider whenever the body is taken upwards. So this is all regarding the downward motion. Now let us try to understand the same when the body is pulled upwards. Again for this, let us consider a same block of mass m, which is tied with the help of a string, and clearly its weight must be acting downwards. The weight of the block mg must be acting downwards, and the tension T must be acting upwards in the string. And now as the block is moved upwards, it must be accelerating upwards. That's it, children. So now the net force acting on the body can be given as sum. Now here which is dominating, children? Upward force. As the body is moving up, upward force is dominating. So the sum of the net force is equals to sum of the upward forces minus sum of downward forces. This is the case. So F net can be written as mass into acceleration, which is equals to sum of the upward forces now is given by T minus sum of the downward forces is given as mg. Okay, so keeping the T this way and carrying the minus mg other side, we have ma plus mg must be equals to T. Or taking the m common, we have m times of a plus g is equals to T. So the tension created in the string is equals to m into a plus g. So earlier case, when the block of mass is taken downwards, it was found that the tension is m times of g minus a, and the same block, when if it is moved upwards, then the tension is found to be m times of a plus g. And clearly as we have this tension is greater than mg now, because tension is dominating. So tension is greater than mg. We feel as if the weight of the block has been increased. Here we feel as if the weight of the block is being decreased, and here we feel as if the weight of the block is being increased. And this can be felt whenever we pull a bucket of water from the well. Is that clear, children? So now let us continue one more model, children. The last model for the motion of bodies connected by a string passing over a smooth pulleys. Okay, well, last example. Let us consider the two masses, say M1 and M2, are connected by a smooth frictionless pulley with the help of a string, and the angle of inclination for the first one be some alpha and the angle of inclination of the second figure be some beta. Okay, so again the same pulley, as it is the smooth frictionless pulley and it is a massless string, the tension acting in the throughout the string must be same, let it be some T. So clearly, let us suppose that the mass M1 is greater than M2. In that case, the body M1 is accelerating downwards and this must be accelerating upwards. So if you observe this carefully, you have this weight of the body is acting downwards, and if you drop a perpendicular here, this will be alpha and this will be M2G cos alpha, and here it must be M2G sin alpha. Similarly, in the second case, if you observe, here you have weight M1G, drop a perpendicular, this will be beta, and here it will be M1G cos beta, and in this direction you have M1G sin beta. So this is the complete figure. So let us try to draw the free body diagram for this and calculate the value of acceleration as well as the value of tension in the string. So it is accelerating downwards. Dropping a free body diagram for this. This is M1 downward acceleration. It is given by M1G sin beta downward force, and upward force is tension created in the string and accelerating in this direction. So clearly we have M1G sin beta minus T must be equals to M1A. This will make the first equation, and coming to the second equation, we have this is your M2. For this upward force is T and downward force is M2G sin alpha, which is accelerating upwards, and the equation for this is given as T minus M2G sin alpha must be equals to M2A. Solving the two equations, we get this minus T and plus T will get cancelled. Then you are left with M1G sin beta minus M2G sin alpha equals to M1A plus M2A. Taking out A as common, you are left with M1 plus M2 into A. Hence the value of A is found as M1 sin beta minus M2 sin alpha times of G by M1 plus M2. Hence the total value is found to be how much, children? It is found equals to M1 sin beta minus M2 sin alpha by M1 plus M2 times of G is the acceleration produced in the two blocks. So if substituting the value of acceleration in either of the two equations, either the first equation or the second equation, you can even calculate the tension produced in the string. Therefore, substituting the value of A in the first equation, let this be first equation, here the second equation. We have from first equation, what is that, children? M1G sin beta minus T is equals to M1 times of A. Instead of A, let us substitute the value as M1 sin beta minus M2 sin alpha whole upon M1 plus M2 into G. So A is substituted. Bringing the minus T the other side, and this term, this left side, we have M1G sin beta minus M1 and G, writing it forward, we have M1G into Leftover term is m1 sine beta minus m2 sine alpha by m1 plus m2 is the value of t. Minus t brought the other side. In both the cases, we observe that m1g is common. Then taking out m1g as common, here we are left with sine beta minus m1 sine beta minus m2 sine alpha by m1 plus m2 is the value of t. So simplifying this, children, you may get the value of t as, the value of t is found to be m1g into LCM, children, m1 sine beta plus m2 sine beta minus, taking inside you have minus m1 sine beta, minus and minus will be plus m2 sine alpha whole upon m1 plus m2 is the value of t.